And welcome to this week's statistics seminar. And today we will have Dr. Pragya Sir from the Harvard University, the Department of Statistics. And her research interest is in high dimensional statistics, statistical machine learning, robust inference, and prediction under multi-study settings, as well as algorithmic fairness. And today, Dr. Sir will talk about modern maximum likelihood theory for high-dimensional logistic regression. So let's welcome our speakers today. Please go ahead, Dr. Sir.
Thank you so much for the kind introduction, and thanks a lot for the invitation to speak here. Although at this point it only can happen virtually, I'm very happy to be here. So this is based on a couple of works. So one of them is joint work with Emmanuel Candes, and the other one is joint work with Emmanuel Candes and Shen Zhao. So the setting for today's talk will be a very classical model that we have in statistics in machine learning. So that is the logistic regression model. So Stats 101, what is this model? So suppose you have a binary data set where the response takes value 0 or 1, and you have a bunch of covariates or features. Then one way to model the conditional dependence between the response and the covariates is by hypothesizing this logistic model where you just use the sigmoid function to model this relationship and using these sorts of inner products. And for this department, I really don't need to motivate how universally logistic regression is used. So this will be the setting for today's talk. And continuing on Stats 101, what we know for logistic regression, as well as many other host of parametric models from classical large sample theory, is if you look at the maximum likelihood estimate in these settings, in these models, and if the number of features P were kept fixed and the sample size diverges, then we know the very classical central limit theorem, which tells us that the MLE, appropriately centered and scaled, is eventually going to be a Gaussian, and the variance is given by the variance covariance matrix is given by the Fisher information. And of course, this assumption that the dimension remains fixed can be restrictive for the different kinds of data sets we see around us today, which are often large and high dimensional. And that naturally has motivated a lot of work in settings where the number of features is also diverging together with the number of samples. And this is really an extremely rich area dating back to the seminal works of Huber in the context of linear regression, which partially initiated this diverging dimension studies in the context of regression models. And so it's almost impossible to survey everything that has been done in diverging dimensions, of course. So here I'm really sort of pointing out the most related works in the context of what I'm going to present. So subsequent works by Portnoy and Hay and Shao, basically what they said was if the number of features is diverging with the sample size, but with a certain relationship, for instance, negligible compared to square root n, then classical CLT still continues to hold if you make the appropriate changes. So if you look at linear combinations here, you will get the corresponding linear combination here. So that's one of the basic staples of classical theory. And another staple is in the context of hypothesis testing, which we all know as Wilks theorem, is if you wanted to test for whether a single coefficient is important or relevant or not, you can compute the likelihood ratio statistic there. And then classical results due to Samuel Wilks also tells us the Wilks theorem, which is saying that this converges to a chi-square distribution if the dimension remains fixed under large sample sizes. And subsequent works due to Portnoy has also extended this to situations where P is negligible compared to n to the 2/3, saying that the same result continues to hold also there, even if number of features were diverging. And so quick recap, if we were calculating p-values based on this result, then if this result continues to be true, if you look at the null variables and look at the corresponding p-values calculated from this result and look at the distribution of the p-values, what you would expect is to see a uniform distribution. That's just by definition, right? And in regular software packages that we use, if you just run vanilla logistic regression, the standard errors, p-value tables you get, we know are based on these, are based on approximations coming out of this classical large sample theory. So we know all of this. Now, today's talk is going to be about the following question. Can we trust this inference when the number of samples and the number of features are either both moderate or moderately large, whereas the ratio remains, the ratio is like 5 or 10. So for instance, you could have a setting where n is 200 and p is 60, or you could have a setting where n is, 20,000 and p is, also comparatively large, keeping the ratio p by n the same, let's say. So this can capture many different settings. So that's the question we will pose today. So to motivate the question, or to get a first level glimpse of what really goes on in these settings, let's look at what happens in some simulation studies. Okay, so I'm going to show you a series of simulations, and the setting in these simulations will be the following. So I'm going to assume that we have drawn the covariates have a distribution. So this is a random design setting. And each entry of the covariates are IID Gaussian, and they are normalized, IID standard Gaussian, and they're normalized so that each column has unit norm. Okay, so that'll be the setting. And the coefficient vector is going to change from one simulation to the next. But what I'm going to hold fixed is the signal to noise ratio. So if I fix the value of the variance of these log odds to some quantity, let's say we fix it to 5, then the SNR will remain the same across all the settings. Okay. And so we have a logistic model. So this is the setting to keep in mind, and I'll show you a series of simulations. Okay. So this is the first simulation. What I'm plotting here so this has n equals 4,000 and p equals 800. So I'm plotting the MLE coefficient estimates versus the true signal. So what I've done is I've ordered the signals by their indices, or the signal coefficients by their indices. So this is a setting where I have chosen the first 100 coefficients of the signal to be equal to +10. The next 100 coefficients are equal to -10, and everything else is 0. So that's the signal that has been chosen. Okay. And the blue points, so the black line basically represents the signal, and the blue points are the corresponding maximum likelihood coefficients. So what you see immediately is that for the positive signal components, for the positive coordinates, the blue points are primarily above this line. For the negative components, they are primarily below this line. And for everything else, they are centered around 0 for the 0 components. And you could ask that, okay, is this something going on as like this is a single simulation run? So is this something that's going on as a special case or no? So we can run the simulation again and again, and you will always see this phenomenon. Okay. So let me show you another setting. So here I'm showing a scatter plot of the maximum likelihood coefficients versus the true signal. Okay. So those are the blue points. And in this case, the signal coordinates are IID from a normal with mean 3 and variance 16. So it has kind of a large variance. And the black line is basically the line with the diagonal, the line with slope 1. And the red line here is a line with slope 1.5. So if the MLE coordinates were centered around the truth, what you would expect when you see this kind of a scatter plot is roughly the black line passes through the center in some sense. But we see that that doesn't happen here. There's a systematic shift, and this red line whose slope is larger than 1 seems to pass through the center of the scatter plot. So these were sort of some preliminary simulations we were doing to try to understand what goes on in these settings. And we concluded from there that it seems that there is a systematic upward bias in the magnitude of the maximum likelihood coordinates. Okay. So then maybe let's have a look at what happens to the variance. So what we can do is we can focus on a single coordinate. Let's focus on a null coordinate. So in this setting, what I'm going to do is I'm going to generate a signal that is half of them are zeros, half are non-zeros. And the non-zeros are drawn from some normal 7-1 IID. It doesn't really matter, but I have half of them to be zeros. So then I focus on a null coefficient. And we look at the corresponding maximum likelihood coordinate, and we resample things many times to obtain estimates of standard errors. So if we look at standard errors of this coordinate, and if we look at the corresponding histogram by doing this many times, then we see that the histogram comes out to be here. So this is somewhere between 4.5 to 5. And this is a setting where I have assumed the design to be random. So we can calculate the Fisher information formula and explicitly calculate what should be the, what does asymptotic theory tell us here regarding what the standard deviation should be. And if we do that, this blue line corresponds to that calculation. So what you see immediately is that there is a massive variance inflation in these kinds of dimensions. And we were not the first people to observe this. This is something that has been observed in the context of linear regression in prior work due to El-Karoui and Donohan-Montanari. Okay. So this is the second observation. And the moment you have this previous observation from the classical understanding that, LRT and, score and Wald tests, they are all equivalent, you should expect that if you look at the LRT, then also some anomalous behavior can be uncovered. So what I'm plotting here is we're looking at a single null coordinate, we're calculating the corresponding negative twice log LRT, and using the chi-square approximation coming from Wilks' theorem to calculate p-values. And we resample things and obtain a histogram of these p-values. So we are focusing on a single null coordinate and doing this many times. So basically, then we get this histogram of null p-values, and we expect to see this to be uniform if the chi-square distribution is a good approximation. But what you see instead is this picture. So let's look at this picture. I mean, clearly you can see that there is a massive spike at 0, and then we have this decay. So p-values are far from the uniform. This phenomenon in itself was observed in the context of a work done by Candace et al. In 2016 in the area of multiple testing. But let me zoom into this plot a bit more and try to unpack what's going on. So what I'm doing here is I'm zooming in the spike close to 0 in the previous plot. So basically in this bin close to 0. And so if I take various target levels in this table, each row corresponds to a different target level. And for each target level, we are calculating how many of those null p-values fall in that particular bin. And we see that, okay, if it were like we would have loved to see a 5% here or a 1% here. Instead, we see here that it's about twice. And the ratio of what we would have liked to see if it were a uniform versus what it actually is, that keeps on increasing as you go closer and closer to 0. So it's not like, the previous plot is kind of at a very high resolution, at a very low resolution level in terms of this small bin on the left. It's not like the phenomenon is going away as you go closer to 0. So this ratio just grows worse as you go closer to 0. And then you can understand this means you will have a lot of false discoveries. And that's particularly problematic for multiple testing applications, which are really common across various disciplines these days. So I have effectively by now shown you 3 phenomena. At the beginning, we saw that the MLE overestimates the effect magnitudes, and that leads to inaccurate estimation if you use classical theory out of the box. Its variability is underestimated by classical formulae. And then we also saw that these p-values based on the LRT are far from uniform under the null. Now, In terms of the literature, yeah, sorry, is there a question?
I have a question about the bias. I think it
Mm-hmm.
was mentioned maybe. So I think the simulation setting here is still where sample size n is greater than the number of variables p.
Yeah.
But even in that case, if p is large,
yeah,
then you are suggesting that the estimation can be biased, right?
Yeah.
The correct interpretation?
That's the correct interpretation.
Yes,
I'm
yes.
not the first person to be suggesting this, as my next slide will elaborate. But yeah, that's what I'm suggesting here.
Yeah, thank you.
Yeah, thank you for the clarification. Okay, so when I went over the literature, you might have noticed I made this huge jump from earlier works by Portnoy and Shao to today. So there is a natural question to ask, are these merely finite sample effects? Because for so far, whatever I've presented to you, counter argument to all of that is, whatever I'm using is really asymptotic theory. So maybe it's a finite sample effect. And there has been extensive work in these areas. And it's well understood that in finite samples, MLE exhibits a bias, LRT requires correction methods. But the understanding in this literature is that if you have small sample sizes, then you need these kinds of methods. So there are classical works by Cox and Snail, Cordero, McCullough, Firth, and so on, who do this finite sample bias. There are sort of lots of theory behind finite sample bias correction and analogous parallel theory for first order correction methods of the LRT due to Bartlett, Box, Cordero, and so on. So let me use one of these existing approaches and revisit one of the earlier plots. So if I try to take the very traditional Bartlett correction in this context, what it does is it looks at the expectation of the likelihood ratio test and does a first order correction. So if you can estimate this first term here, then you can use the corrected statistics, which is just the scaled LRT, which is an estimator of the first order bias. So if you do that and replot the p-value plot I had just before, so there I was using a chi-square approximation to the original LRT, and here I'm using a chi-square approximation to the scaled LRT. Okay, then the previous really sort of concerning phenomenon, it gets moderated to a large extent. So the spike near zero really kind of diminishes. But as you can see, it is still far from the uniform. We are still not at a point that we would like to be. We would really like to see a uniform distribution here. Okay, so these methods actually correct the classical methods to a moderate extent in most cases, but it doesn't go all the way. And that kind of prompted us to investigate this further, that maybe, okay, this looks like it's clearly not a finite sample effect. What's really going on is probably a high dimensional effect in the sense that there seems to be a contribution of having a large number of predictors, even when n is larger than p. Okay, so what is really going on in high dimensions? Let's have a look at that. I'll pause here. Are there any questions? Okay. If there are no questions, let's go on with the talk. So what is really going on in high dimensions? So let me try to summarize all of our results in a single slide here. And this is afternoon here. I think it's almost afternoon there too. So if anybody is sleepy after lunch, it's a perfect time to go to sleep after this slide. Okay, so in classical setting, the number of features is fixed, sample size is diverging. The way we are going to model this particular, the way we're going to capture the high dimensional phenomena that are happening is by saying, let's assume the number of features and sample size are diverging, but they're diverging at the same rate compared to each other. And I'll make that precise in a bit. So P and N are both diverging and diverging at a comparable rate. So the first result that we have is the following. In this setting, if you look at the maximum likelihood estimate, it is no longer centered around the truth. Instead, it is centered around a multiple of the truth. We are going to characterize what this multiple is. And after this centering, in a specific high dimensional sense, it still converges to a Gaussian with a certain variance. And what we know is that this multiplicative bias term, if you will, is strictly bigger than 1. And this variance term is also going to be bigger than the corresponding classical variance given by the inverse Fisher information formula. Okay, so that's one of our results. The
Question?
other, yeah.
Is the asymptotics, is P over N going to a constant?
Yes, it's going to a constant. The constant needs to be positive, and I will say that in the next slide. Yeah.
Okay, thank you.
So the other result we have is the following. So if you look at the negative twice log LRT, then asymptotically in the P over N goes to constant asymptotics, it's distributed as a multiple of a chi-squared, where this multiple is strictly bigger than 1. So if we assume this result is true, now if you calculated a classical p-value using the classical formula, which assumes a chi-square here instead of a multiple of a chi-square, you can immediately see why the classical p-values turn out to be too small, because r is bigger than 1. If you do this calculation, they'll be too small, and hence you have this concentration, a huge spike of the p-values near 0. Okay, so these are the two main results, and for the rest of the talk, I'm going to try to unpack what these constants alpha, this bias, this variance, and this rescaling factor are.
Excuse me, can I interrupt you a second?
Yes, please. Yes, please.
So it's really interesting, and I'm sorry if I'm jumping the gun. Will your theory unify the two? Because for any finite sample, P over N is always a constant. So
yes.
You kind of wonder in your head that they should be sort of a unification of the two, that one slowly goes to the other. Does that make sense?
That makes perfect sense, and that's actually true. So I have a plot later which will say that as P by N is going to 0, our theory goes to, all these constants go to their classical values.
That's what I was hoping. I saw the alpha. I was hoping the alpha would go to 0. As you
So exactly. So this alpha will be, so this is the multiplicative factor. So alpha will go to 1. This variance will go to the classical variance, and this R will also go to 1. Yeah.
All right. Thank you. Sorry about that.
But I have to clarify, we don't have a theory proving that. In our simulations, we always see that's what's happening. But I'll clarify that later in the talk.
All right. Wonderful. Thank you so much.
Mm-hmm.
Sorry, can I have a question too?
Yes, please.
About the same slide.
Yes, of course.
Can I go back one? So when you say the variance in high dimensional is greater than classical variance, is it by the same factor alpha, or is it more than just the alpha?
It's more than just the alpha. So these are 3 different constants. And they're implicitly dependent on each other. Like so all 3 of them depend on the P by N ratio and the overall signal strength you have in the problem, but there are 3 different constants.
Yeah, I was asking because once you see that the centering is by alpha, it's not surprising that the variance should be inflated at least by alpha as well. And that's
So if you do that,
more than just that.
Yeah. So you have that, and there is another contribution.
Thank you.
Okay, so let me lay out the formal setting, because I'm going to look at these kinds of asymptotic situations. So we'll assume that, to abstract things away, we will assume that we have a sequence of problems as N is changing, such that the covariates are Gaussian with some covariance. So I'll have this Gaussianity assumption for the theory, but I'll towards the end show you simulations regarding under what kinds of other distributions the theory continues to apply, sorry. So regarding the dimensionality factors, I'll assume that both of these are diverging, but the ratio converges to a constant. It's important that this stays a positive constant for technical reasons, but we'll empirically see what happens in the limit when this goes to 0. So let me spend a little bit time explaining the regularity condition on the signal vectors. So we don't have any sparsity assumption in these cases, and P is less than N, so things are still identifiable. But we do have a regularity condition, and what our regularity condition is as follows. If you look at the sequence of signal vectors, that is the deterministic sequence of vectors, and if you look at the empirical distributions, then we assume that this sequence of empirical distributions that converges weakly to some distribution that has a finite second moment. Now that's a bit of a technical condition, and if you check things out, this includes a lot of sparse as well as dense signals, but we do need this technical condition. And the other thing I'm going to assume is that the variance of the SNR remains finite in the limit. So the variance of the log odds converges to something. We're going to call this gamma squared through the talk. And in the limit, this is finite, because if this is diverging, then in the limit, you'll have degeneracies and all sorts of weird problems. So just that the SNR is finite in the limit. Okay, so with those assumptions, let's try to see whether the question even makes sense of studying the maximum likelihood estimate. And it turns out it doesn't. The reason is that we are in a logistic regression model, and it is well known that there are many situations for logistic models where the MLE may not be finite. And there is this classical result due to Albert and Anderson, and there have been many follow-up works on this subsequently. That is, if you have a hyperplane that perfectly separates your two classes, then a maximum likelihood estimate is going to be unbounded, essentially. So the question I'm posing only makes sense if we can figure out where the MLE exists or is finite and where it doesn't. So we first need to figure that out. So recall, I introduced these two parameters, gamma square and kappa. One of them captures the signal strength, one of them captures the dimensionality, okay? And what we show is that there is a phase transition curve in the kappa gamma plane, such that below the curve, the MLE exists with probability going to 1, and above the curve, it does not exist. So this can be formalized. We have an explicit formula for this curve, but I prefer not to spend too much time on the exact formula. If there are questions, I can always come back to it. But just know that this is a 0-1 phase transition. Below, the MLE will always exist under the asymptotics I have here, and above it will never exist. So for today's talk, we are going to focus on this situation where the MLE exists. I also have some subsequent work for this other region, which I'm happy to talk about offline, but for today, we are going to just focus on this region below. Okay, another remark that is this point on this curve is known as Cover's point due to Tom Cover, who's a very well-known information theorist for historical reasons. So he had shown during his PhD that this is a point of, if you look at the global null setting where this beta is 0, he had studied that setting, so you don't have any signal. Then kappa equals 0.5 is the point above which the MLE does not exist, and below it always exists. So we are able to generalize that to these other signal strengths. Okay, so now there is one crucial ingredient I need to present our results. So recall, I already told you that the MLE has this bias, the variance is inflated, and the LRT has this rescaling factor in the limit, but we need to describe what these constants are. And the constants are going to depend on the dimensionality and the SNR, the signal to noise ratio. So let me introduce the ingredient that helps us characterize these constants precisely. So I'm sorry for this display. The details are not that important here. What I'm presenting is a nonlinear system of equations, but I'm going to present you 3 main takeaways from these equations. So the first thing to note is this is a system of equations that has 3 unknowns, and I have highlighted the unknowns for convenience. So let's call that alpha, sigma, lambda. One of these, so the alpha will correspond to the bias of the MLE eventually. Sigma will correspond to the variance of the MLE, and lambda also has an interpretation we will see later. So that's why they're named this way. And notice that other than these 3, the system is parametrized by kappa and gamma. So kappa is once again the limit of p by n, and gamma is the limit of your SNR. Gamma square is the limit of your SNR. So what that says is if the system has a unique solution, then you can talk about the solution to the system of equations. And the solution is going to be a function only of the dimensionality factor and the signal to noise ratio. And it turns out that in this regime we are focusing on today, where the MLE is finite, this system will also have a unique solution. Okay, so where we are today, things are like, when I say solution to the system, it's a well-defined object. The solution is unique. Okay, so now let me present our main results. So what is the distribution of the MLE? We sort of worked on this over a series of 2 papers. In the earlier paper, we were looking at IID Gaussian designs, and then we generalized it to designs with general covariances. So what we are able to show is the following. So recall the system of equations I just presented. Let's assume, I mean, we don't need to assume. So so we are in the regime where the MLE exists. So the system has a unique solution. So let's name the solution alpha star, sigma star, lambda star. Okay, it's a triplet. So then if you look at any linear combination of the MLE vector centered around alpha star times the true signal, okay, where alpha star is the same as, so it's the first component in the solution. If you center around this and then you scale by a factor, then it goes to a Gaussian 0, 1. And the factor you need to scale it by is sigma star, which comes from the second member in this triplet, and tau of v. So what is tau of v? So v is the direction you chose here. So v is deterministic. Then this is the variance of, you take the ith row in the design matrix. If you take v transpose xi, and if you take the conditional variance of that, when you have projected out the v direction from xi, that's what tau square v is. And in this Gaussian case, it can be simplified to this kind of a inverse of this quadratic form where this is your precision matrix. So it has a proper explicit description. So that's what we know about the linear combination, distribution of any linear combination. And from here, you can easily work out if you take any finite dimensional, any finite subset or any finite number of coordinates, then what their joint distribution is going to look like. So you'll have the same centering and scaling, and then you need to sort of adjust things by a factor because of correlations among the variables. So if you take the Schur complement of your precision matrix and take that to the -12, then you have corresponding Gaussianity. So what I want to comment is the Schur complement showing up here is not at all surprising. That has a parallel with classical theory. But if you look at classical theory, the extra correction terms that you need here versus that you don't need there is this alpha star and sigma star. Okay, so that's on the distribution of the MLE. Any questions in this slide? Okay. Yeah, so our regularity condition allows for both dense and sparse signals. I have already said that before. So let me provide a few insights into these constants, the alpha star, sigma star. So far what I have told you is they are solutions to some system of equations, but that's not very that doesn't give us any insights. So what we were able to show is that if you take the MLE beta hat, and if you project it in the direction of the true signal, okay, so and if you look at the coefficients, then that converges to alpha star. So what alpha star essentially means is that if you project the MLE in the direction of the true signal, the projection coefficient magnitude, that's not equal to 1 anymore, it's bigger than 1, and that's what alpha star captures. Okay, and the sigma star also has an interpretation. So if you take the MLE and take its projection in the space orthogonal to beta and look at the corresponding norm square, then that's related to the sigma star. Okay, So, and later we were able to generalize this intuition of this is a projection and that's like the norm of the residual of some kind to explicitly say that the residual vector, it's uniformly distributed on the unit sphere that lies in this beta perp space. So that gives us some insights to where these constants are coming up from. This is a quick sort of simulation sanity check. So what we're using is we're using our results to construct confidence intervals for a single coefficient. This is an AR1 design where rho equals 0.5. And we chose this beta transpose sigma beta to be 5. These are the nominal coverages, and this is what the empirical coverage we observe. There's a slight, these are systematically under the target, but the gap is sort of very low, and these are the standard errors of the coverages.
Pragya, can I ask a quick question, please?
Yes, please.
This is going a bit away from your setting, but let's say we had a prior on beta, or maybe just we're regularizing using some penalty. In that case, would you still have like a single number alpha star? Or because I'm thinking there might be situations where you shrink by different amounts in different regions of the beta space. So would the alpha star end up depending on the magnitude of beta in some way?
Yeah, so it will depend on your prior, crucially. But if you choose something like, for instance, IID priors or a prior that is exchangeable on the coordinates, then whatever bias you'll get, you can still summarize through a single scalar.
Oh, okay.
But that exchange, that is important, that the prior treats every coordinate the same way. I mean, if you don't have that, you can't really summarize it by a single scalar. I mean, if you have treats half of them in a certain way, half in another way, you will probably have two different coefficients instead of a single one. So that's the intuition. Yeah.
Thank you.
Okay, so let me elaborate on the LRT asymptotics I had shown earlier. So I already told you that in the limit, the negative twice log LRT will be a rescaled version of a chi-square. So what is this rescaling factor? So this is how the rescaling factor looks like. But note that in this system solution, we had alpha star, which was the bias, sigma star, which was the variance of the MLE, and have not told you about this third component, lambda star, yet, right? So it turns out this third member of the solution actually is crucially related to the Hessian of the log likelihood. So if you take the Hessian of, so this is your observed Fisher information inverse. If you take that and if you take its normalized trace, then that converges to lambda star up to some scaling. And now in classical statistics, what happens is you can write a Taylor expansion for the log LRT. And that involves if you're testing for the jth coefficient, the Taylor expansion for the log LRT involves the jth coefficient of the MLE. So you get a beta hat j square divided by some object, but what you divide by, that essentially cancels out the variance of that coefficient, and that gives you a chi-square 1. But here what happens is in the numerator, you still get this variance of the jth coefficient, but in the denominator, you have a bit of a different quantity. And that happens because in high dimensions, this is a random matrix and its eigenvalues undergo what is known as a certain kind of spreading phenomenon. So that's how this rescaling factor comes up. And so the numerator and denominator do not cancel. So you don't get a coefficient of 1 here. So this is a quick glimpse into what happens if you use our theory and try to compute histogram of null p values. So now you see nice uniform distributions. So that's encouraging. You might actually want to zoom into the smaller p values to see whether the empirical CDF is well approximated by a uniform. So if we zoom into this, there also we see that the approximation is accurate. We have reasonably large N and P here. So you might ask sort of what happens in much smaller values of n and much smaller values of p. So what we find that the asymptotic kicks in empirically, we find that it kicks in pretty early, as long as the ratio of p by n is, let's say, above 0.05. So it's more this ratio that's really important in finite samples rather than the absolute numbers. So if n is a few hundred, p is maybe above 50, the asymptotic kicks in spot on if the p by n ratio is above, let's say, 0.05. So that's typically what I have observed in practice. And then going back to Suhasini's question, that is, does this really approximate the classical works in some smooth way? And the answer is it does. So here what I'm plotting is I'm plotting this bias alpha star. I'm plotting the ratio of the standard deviation from our theory and the classical standard deviation. And I'm plotting the rescaling constant. And in each of these plots, the different colors correspond to different signal strengths. From the right to the left, the signal strength is actually increasing. And on the x-axis, I have kappa, which is the p by n ratio. So what you see is in each of these plots, you see that as the signal strength increases or the kappa increases, then each of these show that each of these constants deviate more and more from their classical counterparts. Let's focus on the left one. So this is alpha star. Classically, this value is equals 1. So as either of these increases kappa or gamma square, these keep on increasing. And the curves look like this because they really asymptote where the MLE ceases to exist. So things blow up there. But in the limit, so when kappa equals 0, we see that this alpha star is going to 1. Our variance is converging to the classical variance, and this rescaling constant is also converging to 1. So we see that in the limit, it seems to recover the classical theory. So because p by n is positive in finite samples, always you can try to use this instead of the classical theory when you're trying to apply this in practice. Okay, so let me recap what I have presented so far. So I introduced a system of equations, which system of 3 equations. Its solution has 3 members. We saw that one of the members characterizes the bias of the MLE, and the variance of the MLE is characterized by another member in this solution, and the conditional variance of each covariate given all the others. And then the log likelihood ratio distribution is characterized by variance of the MLE coordinates and this third member lambda star. Now, the system was parameterized by kappa and gamma, right? So kappa is p by n. So in a real data example, you know what p by n is, but you don't know gamma, the signal to noise ratio, and you also don't know this conditional variances. So we assume Gaussianity for the moment, and if you do that, then you can estimate these conditional variances just using residual sum of squares formulae. But even if you do that, you still don't know the SNR. So I'm going to propose a way to estimate the SNR, which we used. And for that, I'm actually going to use some of our theory. So recall I had presented this phase transition phenomenon, where below this curve, the MLE exists and above it does not, right? And now, whether given any data set, whether the MLE is finite or not, you can actually check it easily by running a linear programming. So this can be set up as a linear programming problem, and then you can check this empirically given any data set. So what we're going to
sorry, but this is, I just missed the chance to ask a question. This is related to the previous slide. So in this kind of setting where the p over n goes to some constant, the MLE is biased by the scalar factor of alpha, and that means it is biased. And does this mean that we may get the unbiased estimate by doing some modification to the MLE, like the shrinking?
Yeah, so you can look at the MLE divided by alpha, right?
Yes.
And that will give you asymptotic unbiasedness. But the issue is that we don't know how to estimate alpha yet. I haven't presented that yet, right? So
Yes,
because alpha depends on the SNR, which is unknown to you. So I guess so if we can estimate that, then you can do this, but you can just debias it by scaling it down by alpha. Yeah.
Okay.
Thank you for the question. Okay, so what we are going to do is use these insights. So suppose we have a data set where kappa, that is p by n equals 0.1. Suppose I have a data set like that. And then what we do is we take this data set, we run the linear program for checking whether the MLE exists or not. And suppose we observe that the MLE exists. So first of all, if you have a data set, the MLE is already infinite. If that happens, then you're not going to use any of this stuff anyways. So suppose we run the linear program, we see that the MLE exists. That means, so you already have some information from this picture regarding what the signal strength could roughly be like. So the MLE can exist only in this region, right? So that already tells you that the signal strength has to lie in this region for your particular data set. Okay, so now we are going to use this fact. So what we are going to do is we're going to take a grid of values, kappa, starting from 0.1 and going higher. Our question is, the signal strength is below this intersection point, but exactly where does it lie, right? So if we take this grid of values, and suppose the next point on the grid is somewhere here. I mean, this is for illustration, you will actually take a very fine grid of values. But suppose the new point on the grid is here, let's call this kappa 1. So what you can do is you can subsample rows from your data set to create a new data set where the value of n increased such that the ratio p by n equals this value kappa 1. And then for this new data set, you can again run the LP and check whether the MLE exists or not. So if it exists, what it tells you is that the signal strength must lie below this intersection point. And this intersection point is lower than this one, right? Because I increased kappa. So that's why you have eliminated this chunk here. Okay. And you can do this, you can subsample many such data sets, then take an average and estimate for what proportion of these does the MLE exist. If the proportion is above 0.5, you declare that the signal strength lies here. And if it is below 0.5, it lies somewhere in between. And you keep on doing this till you hit the first time you find that the MLE ceases to exist. That is, for less than 0.5 proportion of those subsamples, the MLE was existing, okay? So once you do that, you stop right there the first time this happens. And if you have a if you have a very fine grid here, you can interpolate between the previous point and this one to get an estimate of your gamma. So that's the procedure we used for these earlier works. There are actually other procedures one can do, which I've been working on a bit subsequently, but for this work we use this procedure. So you subsample, you test whether MLE exists via a linear program. You record this transition point, and that gives you your gamma hat. But now note that once you have gamma hat, you can obtain estimates for all of these parameters at one shot. Because if you know kappa from your data and you know gamma hat, then you're just going to solve the system of equations we have and obtain solutions to these. And if you took a fine enough grid of values of kappa, because this asymptotics also kicks in very early and this phase transition is sharp, what will happen is if you have a fine enough grid, you'll get a precise estimate of gamma hat. So here it's just an illustration. If I take at the LRT p values or log likelihood ratio, null log likelihood ratio p values. So I'm plotting p values based on the estimated rescaling factor versus the truth. And they are in sort of very good agreement. So this was again n a few thousands, p a few hundred. So that's enough to have a very good agreement of the estimated and the original ones. Okay, so let me show a few simulations to see how robust some of the phenomena or some of the results are to the assumptions on the design matrix. So
can I ask a quick question here?
Yes, please.
Your kappa gamma phase transition plot that you showed, does that depend on, or I mean, in coming up with this, did you use any assumptions in the design matrix?
So this is so for our work, this is correlated Gaussian designs.
Okay.
There have been some work subsequently. One of those works could prove that the same results hold for any elliptically distributed design.
Okay.
I think, but that's to the extent people have theoretically proved it. There is another set of works which talk about general universality in sub-Gaussian designs by Joel Trop and his collaborators. But that is a general theory, I think, that can be directly applied here, but it hasn't been explicitly written in any manuscript.
Thank you.
Okay. So here, the setting, okay, so I'm going to try this out on two real data inspired design matrices. So the first one is inspired by the Crohn's disease data. The source is WTCCC. And what we do is we take a part of the data and we fit a hidden Markov model to a subsample of the data. So what's a hidden Markov model? This is extensively used in modeling these kinds of genetic data sets. So you have some latent Markov chain going on here, and the covariates that you get to observe are functions of these latent Markov chain. And the setting is, so the variable values, the xi values are actually either 0 or 1 or 2. So they're not Gaussian. What we're going to do is we're going to draw the data like this, and then center and scale the columns, center the columns and then scale them to have unit norm. So these are the dimensions. So kappa turns out to be 0.2 here. And the other setting I'm going to show you is a data set from the UCI repository. So this data set is about properties of audio signal files. And so the covariates here are continuous variables. The original data had n to be 500K and p to be 90. What we do is we subsample the data to obtain a lot of covariate matrices such that n is 600 and p is 90, so kappa equals 0.15. So in each case, I'm generating a lot of covariate matrices. The reason is that I'm going to then look at things like empirical CDF of null p-values. So in each case, we're going to do that. So on the left-hand side is the Crohn's disease inspired HMM fit data, and on the right-hand side is the UCI data. So this is the empirical CDF of p-values, and for our theory, that is the blue points. You see that it more or less grazes the red line. There is a little bit of deviation here, but the classical theory is the set of green points. So the sort of issue with the classical stuff that there was that can be fixed by this theory, which even, n and p are not that large. Like this is 690. This is a bit larger, but this is not that large, for instance. So this is one robustness check. And the other, the one thing I want to comment here is what I'm running here is I'm running our probe frontier method and then calculating the p-values. So we are estimating the signal strength using probe frontier, then calculating the p-values. So the next robustness check that I have here is that of what happens if the model is misspecified. And there are two settings I tried. First is when we have, let's say, 1/4 of the non-null variables that are in the 1/4 of the variables that were important while the data during the data generation. I suppose I dropped them. I pretend as if I did not observe them. So that's the setting on the left. The blue points are our stuff and the green are the classical stuff. And the other one is, the data, but it's misspecified in the sense that the link is the complementary log-log link, let's say, instead of the logistic link. So in all the cases, when you do this signal strength estimation using the probe frontier method and then calculate p-values based on our theory, we saw that there are certain settings in which it's robust to the assumptions. So I'm sort of running out of time here. So let me skip a few of these. The comment on this slide is these can be generalized to penalized estimators. So that was done for the ridge regression case in my thesis, and there was a conjecture for a general result there, which in the subsequent very nice paper by Salehi et al. From Caltech, they were able to prove some of the results for the general convex penalties, but you need IID Gaussian design here, so the general case is not known yet. We rely on mathematical ingredients from various different things. So the phase transition relies on stochastic geometry results. The LRT distribution and the MLE distribution rely on results coming from probability theory of statistical physics. And there have been lots of works in all of these areas, which we were drawing upon. So let me wrap up. Sorry, there's some jump that my mouse system. So what I presented today was sort of new limit theorems for very classical estimators, the ML estimators in test statistics, the MLE, the log LRT, and we saw that mainly there are three new phenomena happening. There is this multiplicative bias, there is an inflation in the variance, and there is this rescaling factor one needs in the chi-square distribution. I provided an estimation scheme for the signal to noise ratio estimation, and so we saw how to construct valid p-values, confidence intervals based on these. There are lots of open questions following all these works, and looking at some of them now. Universality or based on the design matrix assumptions, or non-universality thereof, other nonlinear models, model misspecifications, etc. But the techniques we had can be useful broadly in understanding a lot of nonlinear model settings, I think, and a lot of optimization-based estimators. So, hoping that that can be useful in the future as well. So these are the references, but they are also there in detail on my webpage. And thank you so much for your attention.
Okay, thank you very much, Dr. Sir, for this very nice talk. I guess we will have time to take one question for Dr. Sir. If you
Can I ask very fast one question, just because I'm sorry, can I ask one question? It's really fast.
Sure.
So I like your theory is fascinating. There's just one thing that I find really weird. There is a completely unrelated result by Lahiri and his collaborators dealing with estimation for spatial processes.
Mm-hmm.
And they show that they do two asymptotics. They have Wilks' theorem, and they have two designs, and one is called mixed infill, and one is called pure infill asymptotics. So one is when it's completely different. I'll send you the paper. There they also have this weird situation where Wilks' theorem within their design, when it's pure outfill asymptotics, converges to a chi-square distribution with a multiplicative factor. And so throughout your talk, I've been trying to figure out if there was a single link or not.
I see.
And it doesn't seem to be, but it's kind of interesting.
Oh, that would be really great.
Totally unrelated situation has a similar phenomena. It's an analyst paper, and I can certainly send it to you. And you might want to sort of check that paper out too. So I can.
Yes, please. I would very much appreciate it if you can send it to me. Thank you so much.
No worries. Great talk. Thank you very much. Bye-bye.
Okay, so any other quick questions for Dr. Sir?
So I have a quick question. So very nice talk. So could you just briefly comment on what particular aspect of your theory is able to handle this regime that classical, let's say, asymptotic normality of MLE type theory cannot handle?
Yeah, so maybe I can explain this slide a bit because I didn't have time to go over it. So there are sort of two ingredients. So in my earlier work, which was just on the IID Gaussian design, what we were able to show is if you look at the empirical distributions of the MLE centered appropriately, then what is the limit for this object? And to do that, we were building upon what is known as generalized approximate message passing. So this was spearheaded by a paper by Donahoe, Maliki, Montanari in 2009, and then subsequently there have been many other works. So this P order N regime, where you don't assume any sparsity, there are literally not that much tools that can handle it other than a few. So this approximate message passing is one way of going about it. And this earlier result, we actually heavily used for the MLE distribution, even under correlations. So this turned out to be very useful for our more recent paper. And when we were looking at the LRT distribution, there, what I built upon is known as, in statistics, it's now known as leave one out arguments. And in statistics, it was spearheaded by El Karoui and his collaborators starting in 2013. But this has a long history, and in statistical physics and probability theory, it is known as the cavity method. And it's kind of started in '86, following the works of these sort of famous physicists. So, and then Michel Talleyrand is a well-known probabilist who really worked a lot on this area. But people hadn't used it in the context of statistics till these works by El Karoui and collaborators. So for this result, it was these leave one out sorts of arguments that I was trying to do. All of these previous works were in the linear regression context, the statistics works. So there are some subtleties that happen when you go from linear to nonlinear in rigorizing things. So certain things will not work. So there you have to come up with some new things. But basically, it was these set of techniques.
Thank you.
Okay, so I think that's pretty much it for today's seminar. Let's thank our speaker again. It's a very nice talk, and thanks for all of your attention. Bye, everybody.
Thank you so much.